you should see this iLogic site. I will scroll down to the exercises. I will tell you quickly what the syllogisms are. These are kinds of arguments that look like this one. Can you see my mouse? And here we have another syllogism. So these are arguments that have two premises and a conclusion. Their structure is such that they mention three things, the categories as Aristotle would call them. We follow Aristotle because he is the guy who devised the whole thing. The whole syllogistic is his device. What do we have here? We have two of these categories. Here we have P and M in the first premise, and one of them will be repeated in the second premise. The second premise has the categories S and M, and the category that was repeated will not appear in the conclusion. What's the difference between different syllogisms? Is these small words, the quantifiers, all, some, and no, or none. And we can have lots of combinations of them. Here is what Aristotle did. He defined the syllogisms, and he picked up some that are obviously valid. All Greeks are human. All humans are mammals. Therefore, all Greeks are mammals. He picked up some syllogisms like that are obviously valid. What he did next, he used those obviously valid syllogisms to prove many other syllogisms. That way, he was able to express a significant part of ordinary language using his devices. What do we know about the devices? First, we can see that they're symbolic. We have P, M, and S as symbols for some categories. This is why this is called symbolic logic. Then, this logic is called formal because what makes a syllogism valid is not its content, it is its form. So this is symbolic and formal logic. Lots of syllogisms are proven to be valid. As I said, Aristotle took some basic syllogisms. He didn't prove them, he took them for granted. And then he built the whole system out of them. This is a kind of an axiomatic system. An axiomatic system starts with trivial truths and from them builds more and more complex theorems. To prove a theorem, we use a method that is reliable, that is trivially reliable. So there can be no question about that. Nobody can sanely doubt the method. And nobody can deny the axioms, the first truths that we take for granted. This is an axiomatic system. You might know from history that Euclid made an important axiomatic system that we now call Euclidean geometry. He there started with trivial truths. For example, if I have 2 points, I can draw only one line through those points. And other trivial truths like that. The idea of an axiomatic system is very influential, extremely influential throughout the history in philosophy and sciences, because people believed that axiomatic system is a model of a successful science. This is what science has to be. This is our ideal. We do not reach the ideal every time, but this is what we try to do. And people had that ideal for a long time, deep into the modern period. For example, Galileo believed that physics should be built as an axiomatic system. We had to give up that ambition because we couldn't advance in sciences if we had such a strong criterion. And we found some other ways to advance in science without using axioms. For example, quantum mechanics is certainly not a science that starts with trivial truths. It starts with things that nobody can understand. So these are some of the philosophical ideas that go beyond the syllogistic systems. They tell us what is a symbolic logic, what is formal logic, and they tell us about axiomatic systems. Okay, now let us use these diagrams. This is an interactive site, and it can help you check whether a syllogism is valid or not.
So to the right, where it says like minor S, middle M, major P, maybe could you explain what's the use of minor, middle, and major? What's the that terminology?
This is terminology that people who are comfortable with syllogistic use to communicate easily. You're not obliged to remember those terms, but if you find them useful, you can of course remember them. Um, so you can see an example of a syllogism here, and the first term that we have in the first premise is called the major term. And here it is major P. The first term in the second premise is called a minor term. And the term that is repeated in the first and the second premise is called the middle term. We have some examples on this page where the site will go through everything and explain.
Mm.
But I meant to do it myself, so that's why I didn't go to those examples. Let us do the second one. It says all P's are M. Everything that is P is also M. All Greeks are human. Greeks are P, humans are M. Or in terms of sets, everything that belongs to the set P belongs also to the set M. This is what the first premise says. The second one says no S are M, or nothing that is S is also M. or nothing that belongs to the class of S things is an M thing. And then we have the conclusion, some S are not P. And our question is whether the conclusion follows from the two premises. Venn diagrams are convenient for checking validity of syllogisms because if we can draw Venn diagrams for the premises, we can read the conclusion out of the drawing, or we can read that the conclusion does not follow. This is how we do it. The first premise is about P and M. So if I hover my mouse, it will use another color for the circles M and P, for the sets M and P. I can also go over S and M if for some reason I decide to deal with the second premise first. So there are two useful things I can do when I start dealing with this syllogism. I can either deal with P and M, as the first premise requires, or with S and M. So let us go with P and M first. I need to say that everything that belongs to the set P also belongs to the set M, which means that everything within P and outside of M should be empty. And our way to draw that, I will click on this pink line, on the purple line, and these two things will appear. The first one is for shading. Now I will use shading, and I will hover over the two sets, P and M. There are three areas that I can shade. And to represent the first premise, or P's are M, I need to shade this one. This says that everything that is P but is not M is empty. So this part of the set is empty. This is what the shade means. Okay, so far? Let me deal with the second premise. These two things popped up immediately because I have no choice but to use them. The premise says no S are M. So there is no such thing that belongs to the set S and at the same time to the set M. So the section where M and S overlap should be empty. I click on this shade square, and then I have again a choice of three areas where I can put the shade. And to represent the second premise, I need to shade this one. Now, from this picture, I need to see whether the conclusion must be true. Given the shades that have been done, is the conclusion necessarily true? Some S are not P. The conclusion says that there is at least one thing belonging to the set S and not belonging to the set P. Is it so?
Maybe this is where like the language part comes in for me, because according to the Venn diagram that we made, like all S are not P. So would we consider it valid to say some when it's all?
Okay, I'm not certain what the question is. You see, uh, uh, the syllogism is given, and somebody made a choice to have the quantifier all here, and to have no here, and to have some and not in the conclusion. And the question is whether this particular syllogism is valid. We can have a different question whether some other syllogism with other quantifiers is valid. And we should be able to use the Venn diagrams to check all of them.
Maybe this wasn't Kimberly's question, but as I look at it, I think I can do Venn diagrams where it's all P are M, all M are S, therefore all P are S, or whatever, or where it's combining all or none. And then I can also do a Venn diagram where it's like some S are P, some P are M, therefore some M R S, something like that, where we have the common term either all or none, and I see how those go together, and I see how some goes together with other some, but it seems a little odd to go back and forth between all or none and some.
Yes, so to me, that some is a valid argument, but so would none, correct?
Okay, these are just quantifiers. These are parts of the premises. So we don't call them valid. It's the whole argument that is valid or not. So could you please try again to ask me?
It's difficult without it being.
Shall I show the diagrams?
Kimberly, is that what your point is too?
Yeah, I think it's just about, I think Ben's hitting on it and you're hitting on it a little bit of like the switch between the all no and then to some. And it seems odd to have some be the conclusion when the premises allow a more definitive conclusion. Does that make sense?
Yes, it does. So it might be easier if we had a different conclusion that obviously follows from the premises. But
but you would say on that problem we were working, it would be valid. That would be the correct answer.
Conditionally, yes.
Okay, so that's kind of what I was getting at. Like, is the reason it's conditionally because of this discrepancy that we're talking about, or what's the what's the explanation?
Because of this note that popped up here. If the set S is not empty. Because when we have a syllogism, nothing guarantees that there is anything that is S or anything that is P.
So it could be like all flying pigs are P, but then the set of flying pigs is empty.
I see. Okay.
don't take my word for it. I'm asking Professor Djordjevic. He can.
No, that's helpful to say that
Exactly.
that,
All
that could
flying
be
pigs,
empty. We don't know for sure there's anything in that. Okay.
all flying pigs are beautiful. All beautiful things are complicated. So all flying pigs are complicated. This would be unconditionally valid syllogism.
Okay.
But all flying pigs are beautiful. All beautiful things are complicated. And the conclusion this time is some flying pigs are complicated. This one is conditionally valid. In
But
other words, it would be valid if there were
yeah,
flying pigs.
yeah. So, but it doesn't have anything. So the switch from the all, none to some, that's just like the preference of the person that wrote it. Like there's no definitive guidelines for why that switched.
That's a random choice.
Okay.
But there are lots of combinations, and using the Venn diagrams, we should be able to do any combination. Do not feel frightened with this one because I picked up the most difficult example. I wanted to clarify the notion of conditional validity with you. Once you're comfortable with that notion, you know enough about syllogisms for this course. So if this looked confusing, don't worry because I just started with the end.
No, that's fine. Is this the only, is that the only thing that would make it conditional? The idea that there might not be any in that set.
That's it. So it's
That's the only reason it would be conditional.
yes, we call it existential assumption or supposition. That's you don't have to remember that, but in philosophy of language they talk about existential suppositions, and logicians follow those discussions in philosophy of language. So the only thing that the conditional validity depends on is whether there is anything belonging to the relevant set.